Okay.
Alex and David could use entire blackboard. I can. Do I get additional 30 minutes? Otherwise, I will file lawsuit. High discrimination. All right. On that note, so I want to tell you about non-equilibrium field theory. So we'll start from quantum field theory, and then I will go to something more interesting, which is classical field theory. It's a joke. Right. So I probably what Anton said yesterday, I will not convey you too much physics. I will pretty much focus on the techniques. So I basically give you a hammer, and then you can treat your own nails with this hammer. Right? And I will deliberately try to stay clear about all philosophical discussions, whether it is applicable to classes, whether it is applicable to integrable systems, and all that things. So my belief is that the answer is positive. That what I'm going to say is applicable to everything. You just have to be smart enough to apply it. Right? But I cannot prove it. It's just a matter of experience. Right? So it will be about basically practical stuff. All right. So to waste another couple of minutes, what I'm going to tell you was basically outlined first by Schwinger in '58, when Konstantinov and Piret in St. Petersburg, probably not knowing anything about Schwinger, developed similar things in '59. Kadanov and Bain wrote a marvelous book in '62. Keldysh put it in a modern form in '64. And then it was completely sort of swept out of the way by people with sort of larger following, like Gelman, Dyson, Abrikosov, Garkov, Zamashinsky, who convinced everybody that people should use Matsubara, zero temperature, whatever techniques. Right? And that's unfortunate from my perspective, because sort of condensed matter lost a few decades playing with all this Matsubara technique, while one could do something much better. And I'm going to tell you what is this much better story. Right? Good. Okay, so then David helped me a lot yesterday by introducing density metrics. I will keep old name density metrics. It depends on time. Probability operator, if you wish. Now, if you have any observable, which I will call O, be current or density or magnetization or whatever you wish, and you want to know expectation value of this observable at time t, then all what you want to do is to take a trace of this observable, and I'm working in the Schrödinger picture pretty much exactly the same way as David mentioned yesterday, times density matrix of T, and you can have normalization. Okay? Yeah?
Do you mind moving your microphone up a little bit or something? It's just a little bit softer.
Up?
Just either increase the volume or speak a little louder or something.
I would, if I would know.
On your shirt, you want to closer to your...
Oh. That's it. Okay? Better? Good. Thank you. All right. So the density metrics are based on Neyman equations. So what we want to say is that time derivative of rho, and they should look like plus or minus I h of t rho. Right? Yeah. Yes.
T on the row.
Thanks. No, I want specifically have T on the Hamiltonian, right? And that's precisely my point, that in non-equilibrium situations, you generically want to think about Hamiltonian being time dependent, right? Now, with time dependence, there are two very distinct time dependencies there. So one of them is switching off on, I would say, interactions in a distant past of time minus infinity. You want to pretend that the system was simple, non-interacting before creation. Things were sort of Gan-Eden. And then something happened, and interactions was adiabatically switched on. Right? We were expelled from heaven. So there is a adiabatic switching of interaction in a distant past. In the past. Now, typically in equilibrium context, people also insist that there is a diabatic switching of interaction off in a distant future. In our case, we will not have to do any fortune telling, and we don't have to assume anything about future, which I think is a good thing, slightly philosophical. Now, secondly, and more importantly, there are real-time dependence on it, actual time dependence, which come from external fields, changing boundary conditions, and what have you. Right? So, in reality, what I will do, I will always assume that in the beginning, in the distant past, where we still didn't have any interactions, density matrix was also simple and equilibrium. And then it evolved, and possibly evolved to something non-equilibrium precisely because I have some time-dependent fields. Okay? And I think, without, again, entering philosophical discussion, that this is a very generic situation. And it sort of encompasses everything you can think about. But, all right. Good. So what do we do about it? So you can easily formally solve it. Namely, you introduce evolution operator. Which obeys dt u prime. And then with help you can formally solve your density matrix, your von Neumann equation. So you can, this guy was, let me see how I want to write it, u of t minus infinity, rho of minus infinity. So this is a simple thing I see. And then then, provided you satisfy this equation, you can easily check that rho will satisfy this one with the initial condition that at minus infinity you have this simple stuff. Okay. Good. Now, final remark is that this equation you can, again, formally solve and write, say that u of t prime is equal to t exponent of minus or plus minus I into u of t prime to t h of t dt, which is sort of meaningless symbol, but you can make it meaningful by saying that this is a limit at n to infinity, and then you have to say that this is h of minus infinity times delta t this is e I h of minus infinity plus delta t, da, e to the minus.
You don't want to start at minus infinity, you want to start at your initial time is at minus infinity.
Right. Whatever, t prime. Yeah, thank you. T prime. Plus delta t, and this is the h of t now times delta t, and delta t is t minus t prime divided by capital F. Right? And the reason I'm writing all this is because I'm really going to use it in a sec. Okay? Good. Now, now if you go back to your observable, we can substitute this solution into here. So what I'm doing now, I'm taking this, putting it here, and I'm using the fact that I can commute operators under the trace sign. So what you find is that my expectation value of my observable t 1 over trace t. So I will take this one. And I'm using that I can change the arguments and get rid of conjugation. It's a unitary operator. Right. Okay, now couple of remarks. So one is that this thing is actually a completely innocent and simple thing, because you immediately see that trace of rho does not evolve. If you take the trace of this operator, since this is a commutator, trace of the commutator is 0, if everything is okay. So I can put here minus infinity, and since this is a simple thing, which was defined before I introduced any interactions, and disorder to that matter, so this denominator is a completely innocent thing. So I may have a tendency to skip it. Don't worry, there is literally nothing dangerous about it. Okay, but I'll keep it for a while. Now, more importantly, look what we got. So what we got is time evolution along time axis. This is time. And initially with minus infinity, we specify some density matrix. Then it evolves from minus infinity up to time t. At this moment of time, we calculate our observable, right? But then we reverse evolution of time and go back to minus infinity. I'm just reading off what is it there. Right? So you end up with a time contour which has a positive and opposite direction, just in a sense by definition, from the fact that your expectation value has a Bryan cat vector. One of them bring this one, another one bring this one. So you can, in a sense, can't avoid it. Okay? And that's what Schwinger noticed back in 58, and he said that, hey guys, look, we should do something like that. Okay? Now, then other smart people came and say, no, look, Schwinger, look, Julian, we can avoid it, right? And they invented a trick to avoid this story. Okay? So let me, to make a connection with what you probably learned in any standard quantum field theory class, so let me remind you how this trick works, and then I'll tell you why we cannot use this trick in algebraic equilibrium. So the trick is very simple. You simply say that, right, so what you want to calculate, you want to go. So the trick. And to illustrate it, let me be at 0 temperature, and equilibrium 0 temperature, so just ground state field. We can play the same game for equilibrium, but finding temperature. But let's be simple. So then, what you're interested in is to calculate expectation value of your observable over the ground state. And there's no any time dependence. Ground state is ground state. Okay. Now, this ground state is very complicated because this is a ground state of a complicated interacting system. Right? But what you say is that your ground state can be obtained as an evolution from minus infinity to t of some simple non-interacting ground state. And this evolution includes only the first item here, only switching off of the interaction. Okay? So then, what they want you to believe is the following. They say that if you will evolve your ground state from minus infinity all the way up to plus infinity, and you will do some fortune telling, you will say that in the future all the interaction will die out and we'll go back to our initial state, then all what happens is that you will go back to the same simple non-interacting ground state apart possibly from some phase. Right? So there is a sort of assumption of which later was called Gelman law theory. Right? And they say that they proved it, but people still debating whether they prove it or whether they don't prove it, and come up with alternative proofs. But whether it's proven or not, everybody seems to agree that that's the case. That if you think that you very gently switch interactions on, measure your observable, and then switch interactions off, there is no any danger apart from a possible normalization factor.
What about a phase transition, quantum phase transition?
Well, yes, level crossings, you can sort of ask all these questions. Right?
Another answer.
Yeah, that's precisely the point that you deliberately want to avoid
Okay, fine.
discussing. Yes and no, I would say. So, but actually, this, strictly speaking, this Gelman law theorem tells you that if you start from an eigenstate and you evolve it under this adiabatic switching off and switching off, you will end up with another eigenstate, but not necessarily a ground state. Right? And that's about sort of quantum phase transition. You can miss the ground state in some sense, right? So that seems to be dangerous, right? So maybe it's not a true ground state anymore. So maybe there is a danger here, really. But so everybody keep using same quantum field theory. So honestly, I don't know. Look, maybe there is something really, really deep there, but I don't know. Okay, so assuming that there is no hidden skeleton in this closet, so what you can do now, you can say that this expectation value will be 0 u to the minus infinity t. So 0. So then you can stick you can use this thing, rather its complex conjugation, permission conjugation here, and you can write it as e to the minus in 0 e to the ia, so that's a triviality. E to the minus infinity t o u t 0, and now you can stick this instead of this space. So what you find is e to the minus in 0 u plus infinity minus infinity. Oh, I forgot popular demand not to go too far. So then you notice that these two is nothing else but somehow crazy way of going from t to plus infinity. So you first bet minus infinity, but then you say, no, I changed my mind, I go back to plus infinity. Okay? So instead of these two, you can simply stick of plus infinity. And what you get in that already is the following thing. You've got 0 u plus infinity t observable t minus infinity 0, and then you got 0 u plus infinity minus 0. So there are good news and bad news here. So the good news is that you look here, you seemingly avoided having this double contour. You say that you start at minus infinity, go to t, measure your observable, and go to plus infinity. Right? So you don't have to do this, you just keep going. Yep?
Sorry, your propagator U involves the interaction slowly being turned on, is that right?
Yes, in this case, and in this case only, my interactions were 0 when it turned off, and then it turn on and then turn off, right? So that's for this part of the blackboard.
Okay.
So what I'm going to use is only this part of the story, right? I will not assume anything about the future. Right, so that's a good news, and that's how conventional field theory is developed, starting from this. The bad news is that now you have this denominator, right? And notice that the status of this denominator is very, very different from the status of this denominator. So this one really knows only about minus infinity. It's simple and really no danger there. So this one actually does know about interacting system, because on the way from minus infinity to plus infinity, you switch the interactions. Right? So it is purely a phase. It's just another name for it. It's simply this thing. Right? E to the IA is this expectation value. So it seems to be an innocent phase. What it amounts to, it tells you that you should disregard all disconnected diagrams when you do perturbation theory. Right? So that this thing serves to cancel that. But this thing is a major, major headache in a theory of disordered systems. Because what you want to average over disorder is your expectation value, so that's what you want to average over disorder, and it has numerator and denominator, and both of them depend on disorder, because on the way of switching interactions on and off, the exact value of this space does depend on specific realization of disorder. Right? And if you would naively say, that's not a big deal, let me average over disorder base and average over disorder base, you would be in a major, major trouble. Right? So always replica, which Anton probably used, and supersymmetry, which he probably didn't use, and many other tricks were invented precisely to take care of this fact that this denominator does depend on realization of the disorder. Okay? Now, we are going to be in a much, much better shape in this respect. We don't have any denominators to worry about. So the theory of disordered systems will be, in a sense, piece of cake. Very ugly piece. but at least not this stuff. Okay, now more essentially is that if you're really thinking about out of equilibrium, you should throw this away. Clearly that if you have actual time dependence in your Hamiltonian here, then certainly this thing is not going to be true. Starting from a ground state and switching external fields and doing something ugly to your system, you are not going to end up anywhere near your ground state. You will end up with some crazy superposition. So it's not your inability to predict this, it's just that this is not true anymore. Right? And as a result, this nice idea of using single time contours simply fails. Right? And if you are out of equilibrium, you don't have a choice but using this term. Okay? So that's a sort of first conceptual message. Out of equilibrium, you must use evolution back and forth. Okay? Now there is still a sort of nice trick here, namely this idea. And this we can use. We can stick the same thing, let's say here. So we take all that and put it here. And what it does is that you go from minus infinity to time t, where you measure your observable. Then you go all the way to plus infinity, and only then you decide to go back. Okay? So your evolution is still has a forward and backward branches, but you measure an observable on one of them. Okay? Now you can be vigilant and you say, why did you do this? Why don't you stick the same idea here? Okay? So if you do this, then what you will find is that you first of all from minus infinity to plus infinity are abstracted, and then on the way back, you measure your observable. Okay? So you have a liberty of sticking it either here or there, so you can measure your observable here or there. It's still the same time t. Right? Now what you will see is the most convenient way of doing things is to measure it both here and there and take it, if you wish, half sum of the two possibilities. But that's just technicality. You can do it, whatever you wish. Okay? Good. So what we're going now to do is we want to develop quantum field theory where evolution has this two branches. Okay? Now, and I will start doing things from, instead of keeping the observable, I want to be a little bit more simple, so I will throw out the observable. So I will start developing things where this observable is not there. So we will work hard to calculate trace of rho of t divided by trace of rho of t, which is what? So we'll work hard to calculate 1, which I will call fancy name partition function. And in the non-equilibrium theory, and there's no partition function, right? They're not out of equilibrium. So the terminology is vacant, so I'll hijack it and use it for 1. Okay. Now, I mean, it's only a partially a joke, because when we write observables, there is a sort of tendency to write it as 1 over z and then trace of something. Right? That's in our genes. After first year of statistical mechanics, we also know for sure to do it. Right? So I want to emphasize that yes, you use this thing, which you remember by heart, but z is equal to 1. Right? And this is precisely my point, that in disordered system, you will not have it, and then you're in very good shape. Okay? So name is not completely double, I hope. Anyway, so this partition function, quote-unquote partition function, will be what? Just to keep notations. Right, so it will be trace of rho of minus infinity u over c, where c is this Keldysh contour. Divided by trace of rho of minus. Okay, so that's what we are going to do in the next probably until the rest of this class. Okay, good. Now, to do it, I need a Hamiltonian, of course. So I can forget about an observable, but I don't have a liberty to forget about Hamiltonian. Instead of trying to be, general or even interesting, I will pick up the simplest and the dullest possible Hamiltonian. And it's enough to develop all the concepts, so it's a good exercise. So the Hamiltonian I will use is just a single state populated by borders. So this state has energy omega naught, and it's populated by borders. So I can have one boson sitting here, two bosons, three bosons, five bosons. Okay. Or you can call it harmonic oscillator.
No time dependence,
No time dependence, no, nothing. Right? So there's no physics here. I'm saying it's just a formalism. Okay, now as a rho at minus infinity, I will take, as I said, equilibrium one. So I will say that this is e to the minus h minus mu n divided by temperature. So then I will need trace, which is simply harmonic oscillator, of course. So I don't know that. Yeah, by the way, I forgot it on the post. I sent Leo my notes, which is basically just first few chapters of the book. So it was easy to compile. They are posted, and maybe Leo will print them, so you don't have to write all this. So you just can use it. All right. So let's see. So if I want, don't do this. So what is trace of my DAO going on? Probably need to clean up this. So now let's start from the dullest possible reminder. So I have my operators B and B there. They, of course, obey this. So if B and N, I get N minus 1 times what? Times square root of N. And if B there, that's N. So my trace of rho naught of psi n. Just piece of Bose-Einstein distribution. Not quite, but almost. So I will call this thing just rho, or rho naught. 1 minus. Yeah.
Sorry, before we go too much further, can you explain again the philosophy of your Keldysh contour and how you are going to manage to avoid having to say something about the future? That's some important thing I'm missing.
Yeah, it would be nice if you asked before I erased. Look, I used to need to predict future to have this statement that I just erased, that you evolution from minus infinity to plus infinity of a simple non-interacting ground state leads you again to a simple non-interacting ground state. Okay, so now I don't care about it. I know that it's not the case. So even if I switch interactions off after I perturb the system substantially, it's not going to come back. So I don't care. So I switch the interaction on, it stays on here, it keeps staying on here, and then it will be switched off here, if you wish to consider this as a future. Okay, so things happen only in the past, close to minus infinity. At the plus infinity, after I measure my observable, I don't care. Right? And that's the physical thing. Yes.
So formally, your contour is going from minus infinity to infinity, measuring along the way, and then coming back, measuring again, and then switching off.
Well, you can measure it again. You can measure it once here, or you can measure it once there. That's up to you. It's still all the same.
Okay.
Brian, I think what you mean trying to get at is you only need boundary conditions at the ends of the contour, and those ends are at minus infinity.
I see. Okay, and your trick for this is to go into infinity and back. All right. Thanks.
Okay, more questions? Good. Okay. So then I need to give you a reminder what are coherent states. So tell me how many of you do not know how. I got it. So how many of you do not know about coherent states? Everybody knows, right? Okay, so I'm just listing their properties. So you have over complete state of states parameterized by complex number 5. So a few things which I need to stress. First of all, complex number 5. So they are eigenstates of annihilation operator, of course. So this is 5. Then, what do I need from them? So there are a few things I need. So if I have 2 of them, then the overlap is given by phi bar phi prime. Okay? Now, if it's too fast, then don't hesitate to interrupt. Okay. Now, the important thing is resolution of unity. So 1 is equal to integral of t phi bar and phi. And then tell you in a sec what it is. E to the minus phi square phi. Now this measure of integration is nothing else but the u part of phi, the imaginary part of phi, divided by pi, 2 pi, never remember pi. Okay, so that's an important thing. Now, another important thing is trace of any absorber on O can be written again as an integral of phi bar and phi. E to the minus phi square phi matrix element. Okay. So the reason why it's not just this matrix element integrated over all phi, but there is a dating factor is precisely because the system isn't overcomplete. There are too many states. Well, we need a little bit more clever over here. And the last thing I will need to remind you that if you have things like this, all to the power b bigger phi. So rho is a number, b bigger b is an operator, so it's altogether is an operator. Right? And I calculate the matrix element of this operator that I want two different coherent states, one and phi, and another is phi bar. Okay? Then, and this is your first homework to do, is to show that this thing is e to the power phi bar phi prime times this number rho. Okay, so that's your homework. And finally, there is a trivial thing, is if I have my normally ordered Hamiltonian, which is a function of b bigger and b, and that is normally ordered. This is very important. Namely, all b biggers are to the left, all b's are to the right, and I look for expectation value of this guy in phi prime. Right. Notice that this guy is not normally ordered. Because when I will start expanding it, I will have b bigger b, b bigger b, b bigger b. But my Hamiltonian supposedly is normally ordered, and then my life is simple, so I don't have to give you another homework. All b's are acting to the right, all b biggers are acting to the left, so what I immediately got is a Hamiltonian that I substitute phi bar and phi prime instead of b bigger b. So now it's a function, not an operator anymore. And then I have another left phi prime, and we already know what is this operator. So that's all that I need you to recall about coherent states. Okay. So now I can start developing a technique to calculate one. And what I will do, I will discretize my contour. So remember, I told you that with t exponents, the only meaning they have is a limit of n to infinity. So what I need to do, I need to, let's see how I'm going to label them. So I want to say that this is t1 into Tn, then I will have Tn plus 1, and back, and here at minus infinity, I will have t to n. It's t to n minus 1. So I take the entire interval from plus infinity to minus infinity. Of course, you should understand universe have finite lifetime, whatever. So from minus infinity to plus infinity, there is a finite time, and then I divide it by n points, and I have another copy. So altogether I have 2n discrete time events along my contour. Right? And then at each of these time events, I will stick resolution of unity written in that form. Okay. And for that, I will need a complex number phi at each of these time points. Right? So I will have to introduce complex numbers phi 1, phi n, phi 2. Okay. Now, so if I do that, let's see. So let's, for simplicity, think that I have T1, T2, T3, T5, T4, sorry, T5, T6. Right? So my n equals 3, so it's idiotic approximation to a very big number. 3 is big enough. So I want to calculate this. So what I'm doing, I'm calculating trace. So how I'm calculating trace, I need to take expectation value between two of the same coherent states. So look what I'm going to. Is this okay? So I will call this thing which I use to calculate trace, I will call phi 6. And I will go minus infinity. I will have phi 1. And I will have phi 1. So this is my resolution of unity. Then I will have to evolve it at plus delta t. I will have phi 2. Phi 2. Again, evolution at plus delta t. Phi 3. That's another resolution of unity. This is coming from 1, and I'm not writing exponents explicitly. This is 1, so that's 1. Well, these exponents behind the scenes, so remember about them, and just simply not writing them. Okay, so now I came to phi 3, T3. Now I have to go to T4. Now notice that there is no any physical evolution between them. Right? Nothing evolves here. So essentially my evolution operator is 1 here. Now I have phi 4. And then I have phi 4. And between phi 4 and phi 5, T4 and T5, I evolve in an opposite direction. So I will have u minus delta t. I will have phi 5. And this is also 1. This is 1. Now finally between phi 5 and phi 6, I again evolve in the opposite direction, minus delta t. And so I arrive to phi 6 here, and I use phi 6 to calculate my trace. Okay, so that's what I. Understandable? Good, very good. All right, so we're almost done. So the last thing is we need to know what is one of those expectation values, right? So, and we have some with plus sign and some with minus. So there are two intervals evolving in a positive direction, and two intervals evolving in a negative direction. Good. So if I'm asking what is an expectation value of this u plus or minus delta t between two states phi I and j, so then since delta t is small, despite the fact that n equals 3, we still assume that it's small. So I can expand minus or plus. Right, so this sign depends whether I go forward or backward. So this one I can expand. So I 1 minus plus I Hamiltonian delta t j. So now I use the fact that Hamiltonian is normally ordered, so I know how to calculate this expectation value. So this is phi I phi j, 1 minus or plus I h, which is now number phi bar I phi j. And finally, I use my knowledge about overlap of two coherent states written there. So it's e to the power phi bar I phi j. And, oops, I forgot delta t. Now, since delta t is small, I re-exponentiate it back, which is a good thing up to the first order in delta t, which is anyway the order which we are working here. So minus or plus I h of phi I bar j. Yeah, then.
So when you do this contour, you're somehow simultaneously taking the limit where delta t is going to 0 and the length of your contour is going to infinity. Right?
No, I fix the length of my contour, right? Age of the universe is fixed. Okay. And then I'm picking larger and larger n and take this in.
Okay. So it's only at the end that you're going to need the limit of large time.
I mean, in the end or in the beginning, I don't know. From the beginning, my contour is very low, but fine. Okay. And now I divide it by n pieces and take n to infinity. All right. So now what? Look, what we got is that all what we have here. So again, we're calculating 1. So we have a bunch of terms. Each one of them is bringing this thing. It's bringing this thing. Right?
And delta t.
A delta t, yes, thank you. And there is a thing which I didn't wrote explicitly, which is coming from resolution of unities, these things. Right? Now, for my Hamiltonian, I sort of deliberately took an idiotically simple Hamiltonian. So let's write it for my specific Hamiltonian. So this is phi bar I j e to the minus or plus I delta t and the naught phi bar I phi j. Okay. So I have a bunch of exponents in my idiotic examples. All of them are quadratic combinations of phi's and phi bars. Right? That's one thing. So okay, let me go over explode it. So this is 1 over trace over rho minus infinity. Again, this is an innocent thing. I have a product of I from 1 to 2n, d phi I, phi I. That's all my integrations, six integrations here. And then all what I got is exponent, and what is sitting in the exponent is a certain quadratic form of phi I and phi j. So let's see how I want to write it. So what I want to write it is phi sum of j prime from 1 to n, phi bar j, j I j minus 1. So this is certain matrix which I call G minus 1. It's my constitutional right to call any matrix value 1. So I call it G minus 1. G prime, phi, J prime. Okay? And the last thing I need to do is to tell you what is this matrix.
So you're including rho in G?
Yes. Very good. Very good. Very good. So here I am. Here's my rho. Okay. Now again, for the sake of simplicity, think that rho is rather simple. And then what I'm using is this thing. Okay. So it also penetrates into the exponent as a quadratic form of phi and phi prime. Okay, so this, yeah, good point. So this homework is done, is given to you precisely to handle this first term here. Okay, good. Now I have a tough choice what to erase. All right, memorize. Okay, so what I'm now showing you is this matrix I times G minus 1 JJ. So it's a 6 by 6 matrix, or n by n, or 2n by 2n, sorry. So divided by subblocks with the size n times n. Okay, so now it has minus 1 on the diagonal. Now, tell me what this minus 1 is coming from.
Resolution of the identity.
Okay, you memorized it good. Right. So the only diagonal part in this story is coming from the resolution of unities, which I didn't write here explicitly, because all their parts are away from the diagonal. They all involve 6 and 5, 5 and 4, whatever, 3 and 2. So they are in points which are shifted from each other by 1. Okay? So there is non-zero elements of this matrix, one line below the main diagonal. And so there is this element which we'll call H minus, here is 0, and there is H plus, here is 0. So this H minus or plus is simply 1 minus or plus I omega naught delta t. Okay. So now this 1 is coming from overlap of the two component states, and plus or minus identity omega naught come from here. Okay. Here I have 0. Here I also almost have 0, if not for this density matrix thing. Right, so this density matrix thing is coupled between first and last. And what it gives you, according to the identity of homework, is precisely this thing rho naught, which knows something about initial distribution function.
When
Hmm?
you turn the corner, you get a 1.
No.
No?
No. Yes. Right. Very, very good. Thank you. Yes. Very, very good. Good. Thank you very much. So there is this guy where I don't have any evaluation. So that is just okay. So the statement is that 1 is equal to this integral. Can you immediately see it? But we have to, right? Because if it's not, then we are in a trap. So the first thing is really to check this normalization, and it's a useful exercise. So how do I do it? So I have this integral, and I want to calculate.
You have to calculate the determinant.
Hmm?
Gaussian integral.
It's a Gaussian integral, and
One of us got it the determinant.
right. So I, in principle, need to remind you properties of Gaussian integrals. They are in the notes that you will get, so I really don't want to spend time on that. So since it's a complex numbers, it's one of the determinant, not a square root of the determinant, because you have twice as many integrations. So, and integration measure is exactly right. So what it is simply one of the determinant of quadratic form sitting here. So it's I k minus 1. And then there is this guy. 1 over trace of rho f minus. Okay, so what we need to calculate the determinant of this matrix. So what is the determinant of this matrix? Yeah, it's a simple exercise, right? So I have just two terms here. So one term is the product of all the elements. So this is minus 1 to the power of 2n. And 2n is an even number, last time I checked. So this is just 1. And then we have this guy times everything else. Right? So everything else is, and again, it's plus or minus actually. Right, but I want to be double careful about it.
Means the term is off that.
No, I think it's actually minus.
Minus rho 0.
Right. So this is minus rho 0 times the product of all other terms. So what are times product of both. So both one has 1, which is of no interest, and then I have h minus times h plus to the power 2 n minus 1. Oh, not 2. Not 2. Okay. So this is 1 minus rho naught. Now h minus times h plus is 1 plus omega naught square delta t square to the power n minus 1. Now this, if you wish, you can exponentiate. So this is 1 minus rho naught e to the power omega naught square delta t squared n minus 1. Now, delta t, I remind you, was age of the universe divided by n. Okay? So here you have delta t squared. So you have n squared in denominator, only one n here. So in the limit n to infinity, again in that precise sense which I mentioned, that t is kept fixed. These things go to 0. So you got 1 minus, oh no, 1 minus rho naught. Okay. So now we can go here. So this is 1 minus rho naught from determinant. And then, oh miracle, trace of my rho at minus infinity is 1 over 1 minus rho naught. Okay. So they are good. It's indeed 1. Surprise, surprise. But there is a message here. I mean, this limiting procedure is sort of non-trivial. So anytime you have delta t squared times n, you should understand that it's going to 0. But if you have delta t times n, then it goes to refining. To refinement time. Okay? So the way of doing limits here are important. All right. So at least we know to calculate unity. That's good, but useless. But nevertheless, yeah. Look.
In your calculation, how important is the fact that the initial distribution was a thermal distribution?
Yes, that's a very good question. So it's seemingly important because I want to have this form as a quadratic form. Right? If I pick up some ugly nonlinear function, I may not end up with a quadratic. Right? Now, I don't know how to handle it in a simple way. Now, my sincere belief that it's completely what we are going to do, what we are driving at, we are going to derive kinetic equations, and what they will tell us is how the distribution function anyway evolves. Right? And then you can discuss whether initial conditions of this kinetic equation was important or was it not important, blah, blah, blah. Okay? So I don't know to do any better, honestly. But I believe it's not.
But I thought your argument was that it's rho at minus infinity doesn't matter so much as long as you can put in slow evolution into you.
Yeah, precisely.
And evolve it.
Yeah. That's exactly what I'm saying. So I think it's not important. I'm at complete liberty of assuming it and then using it for my advantage. But if you would press me hard to use something else, it would be a little bit more difficult. Yeah.
Do you want to get any interesting information about classical systems in higher dimensions using any of these formalism or no more?
Well, look, I really hope that a bigger part of this course will be the classical systems. So hold your questions. Yes, I talk a lot about classical systems. But, you know, the way I insist, Newtonian mechanics should be taught to freshmen is as a classical limit of final functional integral. No, I'm completely serious. I mean, that's the way classical mechanics should be taught. So let's develop quantum theory and then see the classical as a here. Okay. All right. So the reason I wanted to do this exercise is to sort of start getting rid of this discretization, because come on, enough is enough. How long you can keep doing big matrices? So you would like to have continuous representation, right? Now it's easier to say than to do, but let's at least start doing it. So to start doing it, let me take this. Now you want to rewrite it in a more fancy way. You want to say that this is a functional integral over phi and phi bar and phi, which include all this thing, and I will, from now on, I will not worry anymore about this trace of minus infinity. So you saw it is important actually to maintain normalization. So it is there, but it is trivial. So all that I call d phi bar and phi. And now for this, you invent another smart name, you call it action, which is a functional of phi bar and phi. Now phi bar and phi are fields. It's a set of two endpoints. So far, I have my variable phi and each of these two endpoints. Okay? So I can, instead of having phi j, where j goes from 1 up to 2n, I will say that I have phi of t, but t lives in my Keldysh contour. So far. Okay, so it's double valued construction. Okay, now let's look a little bit more carefully who is this action. It's just another name for that. And you now know what it is. So it's this matrix, it's two diagonal. So this S of phi bar and phi, you can divide it as j from 2 to 2n delta t. Anyway, so now this one, the one. So we have this minus ones and these ones, which I lump into here. So I have phi j phi bar j phi j and phi bar j phi j minus 1. So this take care of this minus 1 and this 1. Okay, so now I have this omega naught delta t, it's here. So the way I write it, I take delta t out and then divide this term by delta t. Now delta t is plus or minus delta t depending on whether I'm positive or negative part of my contour. And then there is a bunch of terms which comes from the things which doesn't fit in this construction. The first term which doesn't have this counterpart, and then it's not term. Everything else I can lump into this. Okay. So then I can say, okay, fine, let me take a limit of n to infinity. Then this sort of reminds you dt calculated along this contour. This reminds you dt of phi. Then this is just since they are almost at the same point, you can say that this is omega naught phi bar phi, the same point. See, you shouldn't worry much about this difference, although it's important that it is. Sometimes we really have to remember about it. And then there are these boundary terms, and you say in continuum representation, probably it's not a big deal. In the limit, it's just one term. So let's try to be brave and close our eyes. Okay? So if you do that, you end up with sort of nice but erroneous statement that your action is an integral over your Keldysh contour dt phi bar t g operator g minus 1 phi of t, and this operator g minus 1 is nothing else but what I dt minus omega naught. So again, dt comes from this, omega naught of course comes from this. Yeah.
What's your interpretation of the last term, in the continuum?
Okay, so my temptation, which is actually very dangerous, is just to do this interpretation. Right? You will see that it's not that innocent. But so far, let's try to do that.
In your previous discretized example, you threw away that remark term. In your previous discretized example, if you threw away that one boundary term, you would just get determinant G is 1.
No, you will get determinant 0. And because I also threw away
you still have the
this.
diagonal.
No, I threw away this. Right. And actually, yeah, that's a very, very good point, which naturally leads me to that. So, yeah, I'm jumping, but it's a good place to discuss it. So this is G minus 1. And it's, of course, not accidentally I chose this name, but eventually we will want to know what is G. Right? So we would like to invert this matrix, this operator. Right? Now, we already showed that determinant of this matrix is not equal to 0. We even calculated it exactly. Right? So it's nice, it's fine. So we can invert this matrix. Right? That we know. So there is some G. Now, with this guy, our life is much more miserable. If you try to invert this operator, you are in trouble. So why are you in trouble?
Zero modes.
Right, there is a zero mode to this operator. I can give you a mode which is either about plus or minus I omega naught t. If you act on this eigenfunctions, quote unquote, with this operator, you got 0. Right? So since there is a zero mode, you don't know how to invert. Another way to express this sentiment is that if you go to the Fourier representation, this is omega minus omega naught. You invert it, you got 1 over omega minus omega naught. This thing contains a pole at the real axis. And you should tell me something how to overcome this. And this trouble we brought upon ourselves precisely by neglecting this step. Right? So the discretized form is nice. There's no trouble there. Right? But once we do this thing, we discretize. Right? So what we're going to do, hopefully get today, is to learn how to stick back into continuum representation this information which was screwed up. So to have a continuum representation free of this uncertainty, how to treat the poles. Yeah.
And to put back this information, you also neglected the fact that the Hamiltonian is 1 at this special point. So at the off diagonal, the one there, because you everywhere you put omega 0, right? isn't the
phi 1 j phi j minus
so
1.
so one of those omega zeros is 0, right? Because your h minus and h plus at the point where you change from h minus to h plus, you have one of the.
It's correctly taken.
This goes away when you take delta t to 0.
But actually it's correctly taken into account in your calculation.
So you're not catching up. So are you worried about switching?
I'm just wondering about. I mean, I see the row the row naught. I see the 1, but I also thought that this omega, that the one term where you
Plus 1.
yeah, this one, yes.
This one.
Yeah.
That's less dangerous.
Yeah, maybe you have a point. Maybe I need to add another term here. Maybe to it, what, n minus n plus 1 omega naught, something like this. Possible, yes. Anyway, so there are these boundary terms which are seemingly absent in a continuous representation.
That one has a delta t on it, unlike these.
Those aren't with delta t.
Those don't, but that one does.
Yeah.
And that's why it's less dangerous.
Maybe. Yeah. All right. Now, before we try to remedy this trouble, let's just do some notations. It's inconvenient to have this integral running along positive and negative. Right? So it is a good idea to go here and split this field into the one which is living in a positive axis. So this you can write as phi plus of t. Probably wanted to keep upper notation, lower notation. See notations. Yes. So phi plus of t, which is for t from minus infinity to plus infinity, and then phi minus of t for t from minus infinity plus infinity to minus. So instead of one double value field, I want to have two fields which are simply living on a time axis. Right. So with that, again, completely formally, this one you can rewrite as dt, and now from minus infinity to plus infinity, phi plus I dt minus omega naught phi plus, and then minus, because we reverse integration direction, minus infinity to plus infinity. So initially I had to go back from plus infinity to minus infinity, I reverse it, so I got this minus sign, and then phi minus phi dt minus omega naught phi minus. Okay, so this is an action, Gaussian action. It's quadratic in phi plus and phi minus. So if I stick it here, it would create an impression that the fields phi plus and phi minus are completely uncoordinated, that I can do my functional integration independently on phi plus and independently on phi minus, and they don't talk to each other. Right? That's another sort of pitfall of continuous notation. So that's a notation which we are going to use, but you should understand that despite of this seeming independence of these two fields, they are dependent because they are connected by this guy and by this guy. Right? There is no block diagonal structure in my matrix. Okay? So what we want to do now, we want to develop a way to take it into account. Okay, good. So to start going this route, what we need to really understand what is a continuum limit of G.
Can I make
Yeah,
a
yeah.
question on that?
Sure.
So, I mean, so eventually you want to use this to treat maybe time-dependent Hamiltonian. So then, you know, the original Hamiltonian say was time-dependent, you may have some parameter that depends on time. So if you include that and go through this procedure, there's an additional correlation that seems like additional relations between the parameters, time-dependent parameters of the, if you wish, Lagrangian of the plus field and minus field, but they have to be equal. They don't evolve forward in time.
Okay, so that's indeed a very good point. So suppose we have time-dependent fields in our Hamiltonian, which we do want to have, right? And now I have Hamiltonian on a way forward and Hamiltonian on the way backward. So what do I think about this time-dependent fields? And you want to have a unitary evolution, right? And you want to have evolve your system under some evolving fields all the way this way. And then you want to unwind this evolution, right? Like playing the movie back. Charlie Chaplin. That's good, right? So you have to keep all the external fields also precisely the same. Right? So your all fields should be precisely the same here and there.
They go back.
Okay, go back. So then your partition function is going to be still 1. Okay, so useless thing. Right? So now how you're going to make it useful? You need to introduce sources. Right? So the standard procedural field theory, you put source term in your action, and then you differentiate with respect to the source, and you got an observable. Right? So source is another external field. Now, if I think that this source field is again exactly the same here and there, I'm still calculating 1. I'm not going to get anything useful. Okay? So the sources, the fields which I use to generate an observable, they should be antisymmetric or at least different between the two quantums. Okay? But they don't have any physical meaning on the first ones, because as we said, all physical fields are the same. Right? So one view on this is that these sources are completely auxiliary things. Yes, you introduce these antisymmetric things, but you differentiate over them once, twice, 3 times, 55 times. And then you put them to 0, and that's the law of nature. Right? And that's, to some extent, true. However, if you want to calculate full counting statistics, namely you don't want to know first moment, second moment, 55th moment of your observable, you rather want to know the entire correlation function, the entire distribution function, right? What people call full quantum statistics. Then you have to keep these sources seriously. Don't take them to 0. So that an additional advantage of this Keldysh technology, apart from doing non-equilibrium, it completely naturally gives you a way to calculate distribution functions as opposed to moments. Okay. So these antisymmetric fields, they play the role of generating parameters for the distribution functions. Okay. So we are going to have them, hopefully. I hope to show you at least one example how to keep them seriously. Okay? All right, so I think you guys already saturated, but and I let you go. But I have a request. So please look at my notes at what is called paragraph 2.5. Because there is very simple but bulky metrics there, and I don't want to copy it on the blackboard. So I will jump up and down about it, tell you what it is about, but I would assume tomorrow that you looked at it and you saw what I'm talking about. Okay? Good. See you tomorrow.